Hello friends, and welcome to a lecture on Cape Open Flowsheet Environment. Today we will learn how to simulate a CSTR. A CSTR stands for or is short for Continuous Stirred Tank Reactor. Now this reactor is fairly common in chemical engineering, but I have found in my entire teaching experience that very few people actually know its application, and this simulator is an effort in that direction. So without delay, let us start. The problem that has been taken is from Design and Control of Ethyl Benzene from William Luyben, AICHE Journal, March 2011, volume 57, number 3. Well, for your reference, here is the paper. I am using this paper under the fair use policy for producing a training video. So this is the title of the paper, Design and Control of Ethyl Benzene Process. The article is written by William L. Luyben. This is the flow sheet for production of ethyl benzene. It is produced by reacting ethylene with benzene. Here we have the first CSTR. This is a reactor. The reaction occurring in the first reactor is ethylene reacting with benzene gives you ethyl benzene. Also in this reactor, there is a second reaction where ethyl benzene reacts with ethylene to give you diethyl benzene. Now, two reactions occur in this reactor. Let us simulate it. To simulate this, we should first know what are the kinetics. And here we have the kinetics in the paper. For ease, I have copied it down. The thermodynamics that we will be using is Peng-Robinson equation of state. The kinetics of the reaction is given as follows. This is the first reaction, the second reaction. These are the values of K, which represent the value of K here for the first reaction and the second reaction. And this is the value of E, which goes in here. Whenever we enter the rate expression in COFE, we should understand that the rate of reaction is calculated in moles per meter cube second if it is a homogeneous reaction. And also the concentrations that go into calculating the rate expression will go in as moles per meter cube. The expression given here has the rate of reaction as kilomole per meter cube second, and the concentration units are in kilomoles per meter cube. Therefore, the rate of reaction has to be multiplied by 1000. That is the rate of reaction when written as an expression like this, taking these as the constants. The rate of reaction that has to be entered, the expression that has to be entered to COFE is the expression that we would write this way. We have to multiply it with 1000 and we have to divide the concentration units with 1000. We have to multiply the rate expression with 1000 because the rate expression is in kilomole per meter cube second. And we have to divide the concentration units with 1000 as the concentrations here are in kilomole per meter cube. Doing this, we get the following rate expressions, which can be directly entered in COFE. Now, I have already done the simulation, but I shall explain it once again. Let's go back to the article. We find here that the fresh ethylene is 630.6 kilomole per hour, which enters the reactor number 1, and the benzene is nothing but the sum of the fresh benzene and the recycled benzene. We take these amounts and enter it in feed stream number 1. The pressure is 20 atmospheres. The temperature is 320 Kelvin. The total benzene entering the reactor is 1598.9337. The total ethylene entering in is 630.69694. Ortho-diethyl benzene entering in is 0, and the ethyl benzene entering in is 0.9694. Now we connect this stream to the CSTR and we draw an outlet stream from the CSTR. How to do all this? That is, make streams, enter their values, and connect streams to unit operations is given elsewhere in the playlist. Please have a look in the playlist and you shall find all the videos regarding this. Now let's get back to the configuration of CSTR. In the configuration of CSTR, we double click on the CSTR icon and get this window. We click on edit. The pressure drop obviously is 0. The reaction is taking place isothermally at 434 Kelvin. The enthalpy balance that we use is enthalpy F. Now we go to the reactors window. The reaction phase selected is liquid and the reactor volume entered is 200 meter cube, which is given in the article. Now we go to reactions. For clarity, I shall delete this and demonstrate once again. In the reactions window, we click add and we select both the reactions. Now we again click edit. Ensure that we have entered the reactions. Solve options are left as it is. And we close the window. It may happen that when you are attempting to edit and click add, you may not find the reactions here to add. This can be solved by right clicking on the icon and going to assign reaction package and assigning the reaction package by selecting it. Now we are all set to simulate. Let's go ahead and run the simulation button. We have simulated it. Let's click on insert, stream report, click on stream report, select the streams, go to overall properties and select component flow of ethyl benzene, component flow of ethylene and component flow of diethyl benzene. Let's take ethylene on the top and click OK. What we find here is that 630.697 kilomole per hour of ethylene entered into the reactor and 6.12536 kilomole per hour is leaving the reactor. It means ethylene has reacted. The conversion is about 90%. This conversion is for production of ethyl benzene, which is 407.818, which when you reduce by this amount is roughly 406.818. And the orthoethyl benzene, diethyl benzene produced is 108.862. As we can see that the selectivity is towards formation of ethyl benzene. So this was a short video on simulation of CSTR. You can find more about this problem by going to www.capeopen. Click, select COCO simulator, go to sample flow sheets, and you will find that the problem has been posted here at the end. This has been contributed by Professor Arvind Prasad. I am Professor Arvind Prasad. If you click on preview, you shall find this window, and if you click on this, you can download the flow sheet and practice it for yourself. So that was all about the simulation. Thank you guys. Have a great day. Goodbye.